So today's about the Riemann sphere, three of the most common models of the Riemann sphere. One is the extended complex plane, which is a space that results from adding a point at infinity to the complex plane. The complex projective line, which is more algebraic, and the unit sphere, which I guess like all of you have seen already at some point, right? I mean, that's the easiest to visualize. So let me start talking about the extended complex plane. So as I said, the extended complex plane is the result of adding a point at infinity to the complex plane. Right? So I think there's not much to say about that, right? One can try to visualize. You see kind of a sketch like, okay, so this is the complex plane, and the other point is just outside, and it's kind of in a way infinitely far away, right? So this is one way I like to visualize it. And then I put a topology in it. So I define what the open sets are. Right? Does everyone know what a topology is? Has everyone seen the definition of the concept of topology? Yeah. Okay. And the topology is actually not very complicated. So the open sets, well, first of all, you see, I'm really attaching only one point, right? Only one point. That's the kind of the whole difference between this C bar and C is just one point, right? So of course I would like the open sets of C to be open here, right? So I just declare them to be open, and I take this other class of sets and I declare them to be open. So what I do is I consider the compact subsets of C, right? So the compact sets that are kind of in the plane, right? And then I take their complement in C bar. So their complement in C the point at infinity is part of that complement. And those I declare to be open as well, right? And then kind of if you want to start already thinking about kind of that is the complex plane and somehow that one really wants to have a sphere, you can think that this should be the case in order for us to actually obtain some sort of sphere, right? That the opens that contain infinity can be obtained by chopping off just compact complements. Right? And so somehow this is meant to sketch that situation, right? So where here as you see, I am sketching the complex plane, and then here kind of the point at infinity outside, and here I have my open subset of C, and in this other case I take a compact subset of C, and then the corresponding open set is actually all of this, including the point at infinity. Okay, so this is kind of just sketchy, kind of the purple kind of this purple kind of purple. Both of them are purple, right? But this kind of these purple sets are the opens in the open sets in C bar. And of course, kind of there is of course the first thing, right? Is this indeed a topology? Well, exercise. Right? It's actually an easy exercise. C bar turns out to be compact under this topology. That is, every open cover of C bar by opens belonging to this tau has a finite subcover. Right? And well, of course, it should be expected that C is dense in C bar, right? I mean, kind of given this, right? And given that infinity just by itself is not an open subset. Okay, so this is one exercise. One nice thing about this model is that one can very easily see that it is a Riemann surface. So one can very easily give an atlas, a collection of holomorphically compatible charts. Has everyone seen the definition of Riemann surface or holomorphically compatible charts? If not, that's okay. I mean, yeah. If you haven't, I mean, you shouldn't panic. I mean, it's okay. So, what I want to say is that it is possible to cover C bar with two special open sets, namely C, which is we declared it is kind of one of the obvious open sets in C bar, right? And with C bar minus 0, right? I mean, of course, 0 forms a compact subset of C, so its complement is open in C bar, and then you see it's kind of C bar minus 0 should actually is kind of, you see, it's kind of, we take C, we attach another point, and then we take off one point. So this C bar minus 0 somehow should look just like C. Right? It should look like kind of C is seen as from another angle somehow. And that's somehow actually what happens. We have these two distinguished, or these two special open subsets of C, and then from this one, we of course have the identity to C, which is a homeomorphism, and from C bar minus 0, we have this homeomorphism to C, which is 1 over Z, right? Which is just taking inverses, and somehow, of course, with the convention that 1 over infinity would be 0 for this I. And what happens is that in the you see in the intersection of these two, which actually is just like one is kind of like C, but punctured, right? without the origin. That's the intersection of these two open sets, and one has from that intersection. So let me write it: C intersect C minus 0. From that intersection, one has this function. The first function goes to C, and to C, and its image is again C minus 0, right? Because I'm taking this point off, and from here we also have C minus 0, which is the restriction of I. The restriction of I to this intersection, and this is C bar minus 0. And the point is that this composition, which is somehow the change of coordinates, is holomorphic, right? And that's when I call two charts holomorphically compatible, when the transition functions or the change of coordinates are holomorphic. The point is that whenever one has a space, like let's say a topological space, let's say Hausdorff topological space with a countable basis, and one can cover it with certain open sets, and one has functions and such that the transition functions are holomorphic, one calls the space a Riemann surface. And somehow the idea is that locally the space looks locally as just the complex numbers. Right? And one thinks of these functions as certain type of local maps in the space. Okay, and so I'm going to leave this as an exercise, and as an exercise I leave that you see that it's these transition functions that are holomorphic. That's the exercise, and that exercise is actually very easy because it's really just showing that this one is holomorphic. And remember that a function is holomorphic if it is differentiable in the complex sense at each point. Okay, so a little bit more, something that is kind of a bit more advanced, but also kind of I wouldn't want you to panic. Is that one can define the genus of this space to be a certain number. So it's kind of it's the dimension of certain vector space, which is the first cohomology group of this Riemann surface over the sheaf of holomorphic functions. Okay, so that's a mouthful, but somehow my point is that certain number can be defined, right? And this number is kind of the definition of this number is compatible with what you know already about, like that the torus has genus 1, for instance, and that when one has something with two handles, it's genus 2, and so on. My point in including this remark is that there are ways of saying this kind of in a very formal, of defining these numbers in a very formal way. And a consequence of one of the very famous theorems in the theory of Riemann surfaces, the Riemann-Roch theorem, what it tells us is that one consequence it has is that whenever one has a compact Riemann surface of genus 0, right? So C bar is a compact Riemann surface, right? And one can prove that it has genus 0. Well, it turns out that whenever one has a compact Riemann surface of genus 0, it is automatically biholomorphic to C bar. So there is a bijective holomorphic function from that Riemann surface of genus 0 to C bar, and with holomorphic inverse. And somehow all this means is that with the extended complex plane, what we have done is precisely find the unique Riemann surface of genus 0. Okay. Okay. Again, if you haven't heard, if you don't know what the Riemann-Roch theorem is or so on, kind of don't panic. I mean, I'm going kind of maybe right now everything is a little bit of a mouthful, but I'm going to be kind of coming more down to earth very soon. Something which turns out to be very important is the notion of when a function going from an open subset of the extended complex plane again to the extended complex plane is holomorphic. In your complex analysis course, I mean, from what you saw in your complex analysis course, you know what it means for a function going from an open subset of C to C to be holomorphic. Now I'm talking about something slightly different, slightly more general or slightly different, because now I'm allowing open subsets not only of C but of C bar, of something a bit bigger, right? Something a bit more general. And now I'm allowing to arrive at not the complex numbers, but the extended complex plane. Okay, and such a function, one says that it is holomorphic if certain compositions are holomorphic in the usual sense that you already know from your complex analysis class. And somehow the idea is that you have your subset V of C bar. Right? It may have the point at infinity, and somehow that's the point where one could say, I still don't know what it means to be holomorphic at the point at infinity. Okay, so what one does is one takes in C bar we have our two special open subsets, and then one takes either of them. Well, I mean one takes each of them at a time. Let's say that I take U2, right? And then somehow what I do is I see the part of U2. Sorry, I'm losing the train. Right, sorry. Yeah. So one takes U2, and then one takes the part of U2 that kind of that overlaps. No, sorry, I'm screwing up. No, one takes U2, which is an open subset of C bar. One takes its inverse image on the function we are dealing with, about which we want to say what it means by definition to be holomorphic. What's the definition to be holomorphic? Okay, and then this inverse image somehow you see in V, in my open subset of C bar, this inverse image kind of it has somehow like two overlapping parts. One part which has in common with U1, and the other one that has in common with U2 itself. Right? And then one takes each of these two. I mean, this is with U1, but one can also take U2. And somehow my point is that this whole inverse image can be recovered by considering the part that it shares with U1 and the part that it shares with U2, which then gives me the whole inverse image. When one takes the part that it shares with one of them, that part one can simply send to C using the coordinate function, or the function from the chart, which are one of these two functions. And then the point is that one lands already in C, and then one can ask whether this composition is holomorphic or not. So, and one defines the function to be holomorphic if that's always the case, if those compositions are always holomorphic. So you see somehow what I mean is you declare a function from an open subset of C bar to be holomorphic if every time you take one of these special open subsets that we saw, and we split it into the part that goes with each of the two special open subsets, whether the corresponding compositions are holomorphic. If they are, then you call your function holomorphic, right? So somehow you check the possible holomorphy locally. Okay, and this okay. This notion is going to be very important because whenever a function is holomorphic, it will be conformal, which is that its derivative is going to preserve angles at the level of tangents of tangent spaces. Okay, and that's going to be something very important later on. Okay, and then one has the notion of what a meromorphic function is. Once one has a notion of a holomorphic function, and meromorphic functions on a connected open subset of C bar turn out to form a field. I'm not going to say much about this, except that the proof follows from two very strong theorems of complex analysis. Right? The Riemann's removable singularities theorem and the theorem of the identity. Right? So for instance, the theorem of the identity says that if you have two holomorphic functions defined on this open connected subset V, and they coincide in a set of points that has an accumulation point, then they are automatically equal. Right? Okay. Right, and then somehow this kind of formalizes the fact that if whenever one has two polynomials and one and kind of one of them is not zero, so that one can put it as in the denominator. Considering the function from C bar to C bar that in each complex number that to each complex number set sends to f of z divided by g of z, that this is actually a holomorphic function, which you probably saw in your complex analysis course. And this is one way of embedding the rational function field, right, where x is just an indeterminate. I mean, x would formally not be a complex number; it would just be an indeterminate, into the field of meromorphic functions defined on any open subset of C bar. Well, here two exercises which are kind of really kind of so that you recall or review a little bit of your complex analysis class. So here I take two non-zero polynomials, and I take, you see what this, by this I mean the one-dimensional complex vector subspace of the vector space of polynomials spanned by f. That's what I mean. Same thing here, right? And so what I mean here is that this one-dimensional subspace is equal to this one-dimensional subspace. In other words, that f and g are linearly dependent as polynomials, and so these are linearly dependent as polynomials. So one is multiple of the other, right? If and only if this quotient function is constant. Yeah, and then this other exercise, what I'm asking you to do there is that every meromorphic function defined on the extended complex plane is actually a quotient of two polynomials. Okay. I mean, here I'm saying that the quotient of two polynomials defines a holomorphic function, so a meromorphic function. And here I'm asking, okay, every meromorphic function defined on C bar is of this form. If you have a look at Liouville's theorem, this is actually not very hard. Yeah. Okay, and then the notion. Okay, so So all of this has been about holomorphic and meromorphic functions, and I don't know, maybe it's a bit, maybe it's a bit too abstract for the first class, but okay. So now let's try to go back down to some concrete stuff now. Circles in C bar. So the notion of circle in C bar is actually quite simple. It's either a circle in the plane, in the complex plane, one of the circles we are used to draw, or a set of the form straight line, Euclidean straight line, union infinity. Okay, either of those two things I'm going to be calling circle in C bar. Right? So somehow some examples would be, well, of course, this is a circle in C bar because it's simply a circle in C, and then this line union the point at infinity, that would be another circle in C bar. Okay, so that's my new notion of circle, and the notion of open disk. An open disk is going to be, well, if you take a circle in C bar, you can see in either of the two cases that it splits C bar into two. In other words, when you take the complement of the circle in C bar, that complement has two connected components, right? And somehow, kind of in this case, it's very easy it's really easy to see because it's kind of just the interior and the exterior, if you like. Right? So each of those connected components I'm going to call an open disk, right? But here it's the complement in C bar. So somehow here all of this together with the point at infinity, I call an open disk. Okay, and in this other case, it's the complement of the circle, right? So this is an open disk, but without including the point at infinity, or the other connected component also without including the point at infinity, right? Because the point at infinity belongs to this circle in C bar. Okay. All right. So that's about the extended complex plane, which somehow my main point is that there we have that it's a Riemann surface, and we have a new notion of circle in C bar. Right? So that's kind of the main two things I want you to take away from that. And that is one model of the Riemann sphere. Now I'm going to go with the second model, which is the complex projective line, which as a set is simply the set of one-dimensional C vector subspaces of C2. Okay, so this P1C, the complex projective line, its elements are what are the vector subspaces of C2 spanned by non-zero vectors. Okay. Okay, and then I also put a topology on it, and what I do is to put a topology on this set. What I do is I realize that for this one I have a topology, like the analytic topology. Right? So by analytic topology I mean the topology whose open sets are those that can be written as unions of open Euclidean disks. Right? So the ones from complex analysis, or if you want the ones from calculus from several variables. I realize that, and I realize that I have this obvious surjective map, right, which to each non-zero vector associates precisely the one-dimensional vector subspace it spans. right? So this is, I would say, this is an obvious function, right? So that's why I call it tautological function. It is clearly surjective. And what I do is I topologize this space in such a way that this tautological map is a quotient. It's a quotient. Okay, I didn't want to say the word category, but it's an identification map in topology. Yeah, has everyone seen the notion of identification in topology? When a function is an identification?
I'm not sure.
No? Okay, so the way we topologize this is the following. So first of all, we want it to be continuous, right? I mean, kind of, because it's a natural map, so we want it to be continuous. So first of all, we want the inverse image of anything that we declare open has to be open, right? But then one can say, then one can say, okay, so you have an easy answer. Take just the empty set and the total space to be your open sets. If these are your only open sets, of course, inverse image of this is open, and inverse image of this is also open. But that's kind of a silly topology, right? Because it's kind of, I don't gain anything. Then I say, okay, you better put more opens, right? So you start putting more opens, and the only thing you have to be careful about is whenever you say, okay, I put one more open set, you have to be careful because you want the inverse image to be open. Okay, and then you say, okay, then how about this? Let the open sets here, by definition, be precisely those whose inverse image is open. Right? That's going to be that's going to have the property of that this is continuous. And second, you cannot put more open sets, right? Because you are putting everything you could. Okay, that's the topology I put, and that's the topology that makes it an identification. Right? And the word identification kind of really comes from the fact that with that topology, somehow this map satisfies certain universal property. But I don't want to go into universal properties today, or maybe even in the course. So is it clear now what topology we put here? Yeah, I mean, at least conceptually, what is that we require from these open sets? Yeah? We declare to be an open set every single subset which with the property that its inverse image is open. Okay, and then some exercises for those of you who have seen the Zariski topology. The Zariski topology in C is kind of quite easy. It's kind of just the complements of the finite subsets. Right? And somehow the exercise is what's the relation between the analytic topology, so the one coming from calculus, let's say, with this topology whose open sets are precisely the complements of the finite subsets. And the corresponding exercise, but not for C, but for the complex projective line. Okay. All right, and now I'm going to describe the points of the complex projective line in a slightly more concrete way than this one. Okay. I'm going to describe them in a way that allows me to obtain certain parametrizations, certain natural parametrizations of the complex projective line, and kind of that at least allows me to justify why am I calling it line, right? It should be something one-dimensional, so there should be something of only one parameter somewhere instead of these two parameters, right? Anyway, so that's what I'm going to do now, to describe the points in the complex projective line in more concrete ways. For that, take an ordered basis of C2. Right? So every non-zero vector can be expressed as a linear combination, of course, of the basis with complex coefficients. So this way, right? And since the vector is non-zero, you know what? I know that at least one of the complex numbers, alpha or c or beta, is non-zero. Okay, now obviously, if beta is not zero, I can divide v by beta, and when I divide v by beta, of course the vector changes, right? So I'm obtaining another vector, but the vectors, the one-dimensional vector subspace it spans in C2 doesn't change, right? V and v divided by beta span the same vector subspace of C2, right? So I really have this. And if beta is 0, then here this is 0. So now I can divide by alpha, and the vector changes, but the vector subspace it spans doesn't change. Right? So I have this. So what I see is that once I took my ordered basis, every element, every point in the complex projective line can be written either like this or like this, right? So every point in P1C has either of these two forms. This Z V1 plus V2 for some Z in Z, or right, and then so what I see is that the points in P1C in the complex projective line can be fully parametrized using just this parameter. Once I agreed on which ordered basis I'm going to use. Okay, so what I just said really is that this function that goes from C bar to P1C, that you see for each complex number considers this corresponding subspace, and for infinity considers the other one, that function is surjective. That's what I just said. I mean, what I said is just that. Well, it's not only surjective, it is actually injective. And it turns out to be a homeomorphism between the extended complex plane, so C union infinity, and my complex projective line. And, well, the fact that it is injective and that it is a homeomorphism, right, is I leave as an exercise, knowing that once you show that it is injective, to prove that it is a homeomorphism, you only need to prove that it's continuous and that it's open, right? That it sends open sets to open sets. So kind of once you know it's bijective, showing that it's a homeomorphism is kind of at least clear what one has to do, right? It's not very complicated. Okay, and here, here. Yeah, so here let me show you. Yeah. So somehow, you see, let me write here. Oops, sorry. Let's say that this is actually V1. And then this other is V2. Right? And kind of, I'm just going to try to explain kind of what this means kind of visually. Okay, so of course I cannot draw C2, right? I mean it's 4 real dimensions. So what I do is kind of, okay, I only draw R2, right? Or if you want, only kind of the real parts, right, of the vectors. And somehow you see what happens is that, for instance, this gives me an element of the complex projective line, right? By this I mean I'm kind of just sketching a one-dimensional vector subspace, and you see this point, if you think about it, that point really is, you see, so let's see, this really is Z, right? If you think about the law of the parallelogram law to draw for the addition of vectors, right? Because you see this vector is obtained by adding this vector, which is V2, plus that vector, which is V2, with some non-zero multiple of V1. So this vector that you are seeing here, this vector that you are seeing here is actually of the form V2 plus Z times V1. So Z really is, as you like what you just saw there. So Z is somehow just this kind of scalar magnitude. So what am I saying? That what this represents in kind of in for the inverse, right? So in order to from the one-dimensional vector subspace to recover the scalar, what that amounts to simply taking the one-dimensional subspace and seeing where it crosses the copy of R, or the complex numbers, sitting at height 1 in V2. That's what I mean. Somehow, what one does is one puts a copy of the complex numbers at the tip of V2, and then the one-dimensional subspaces, one moves them around and see where they intersect this copy of C sitting at height 1 in V2, in the tip of V2, and where one intersects, that's the Z. Right? So somehow this C bar is kind of C sitting at height 1 at the tip of V2, of the second vector. At least under this function, right? Under this function. Okay. And finally, well, if there are no questions, so somehow let me see. So what should you keep in mind about the complex projective line? Well, the definition that it's as a set is just the set of one-dimensional vector subspaces of C2. Right? So this is really like an algebraic definition. Right? And that its relation, it has certain relation with C bar, right? And that relation can be obtained by placing a copy of C at height 1 and intersecting the one-dimensional subspaces with that copy of C. So that's another model of the Riemann sphere, and let's say a little bit about kind of the most concrete one, right? Just the unit sphere sitting in R3. So the points in three-dimensional Euclidean space, right, at distance 1 from the origin. There's not much to say, so I'm going to switch to the other notes. Sorry. There's really not much that one needs to say about the topology, right? I mean, it's a subset of R3, so just topologized as a subset of R3. And just as in the case of the complex projective line, I'm going to immediately look for a relation with C bar, with the extended complex plane. And that relation, you see, what I can see is, okay, somehow there is an obvious plane sitting here, right, kind of like cutting the equator of the sphere. And something I can do is, let's say, just project, right? So kind of take the north, consider the North Pole, and start projecting, right? And then, like, kind of the North Pole, let's say from the North Pole I go, and then when I go down, you see I cross this point of the sphere, and then I cross this point of the plane, and then I can say, okay, so that's the way they correspond to each other. Right? And then, for instance, the south hemisphere somehow corresponds under this projection, right, to the unit circle here, right? Yeah. And that's what we do, and we call that the stereographic projection. And one can it's actually very easy to find what the rules are, right? So what the explicit formulas are. So in going from the sphere, in projecting from the sphere to the plane, right? So one goes from 3 variables in R3 to just a complex number, and finding this formula is actually very easy. So I didn't write it as an exercise, but it is a very educational exercise to deduce this formula. Okay, it is quite simple, right? Because somehow what one anchors at the North Pole at the point 0, 0, 1, and then one starts going, and then one crosses somewhere, and the point is that you see this vector is a real multiple of this vector. So one has to find the correct scalar, right? And when one finds the correct scalar, one plugs in, and then one arrives at this formula. And if you want to go the other way around, right? So if you take you take one straight line through the North Pole, and then you want to see which point in the sphere corresponds to this point, you realize the same thing, right? So this vector in R3 is a non-zero multiple of this other vector in R3. And you find the corresponding scalar, and then after finding that corresponding scalar, you arrive at this formula. Okay. So I leave you as an exercise to derive these formulas. Right? I mean to deduce these formulas. So. Okay, and then here you can see some more examples, right? To this point, one goes to this point, and from this point in the unit circle here, one goes to the south hemisphere, and so on. And these two functions are actually mutually inverse, right? I mean, and showing that they are mutually inverse. It can be done in two ways. One way is you can say, okay, it's simply because these formulas, what they tell you is precisely this of first you go, and then like first you go from here to here, and then you come back. Right? So those formulas should really give you inverse functions. Or the other way to show that they are inverses is just doing the computation, right? Either way. And what is a bit more challenging is showing that they are actually diffeomorphisms. And this is actually challenging. Well, in the end, that they are diffeomorphisms between S2, between the unit sphere and the extended complex plane. In the very end, it's because all these, everything that appears in numerator and denominator are polynomials. That turns out to be kind of the very final reason. But the details I leave as an exercise. Okay, and just as in the case of C bar, here we also have circles, right? And the point here is that there are kind of at least two seemingly a priori seemingly different ways of defining what a circle is in the sphere, right? One can say, okay, a circle in the sphere is just take a plane that cuts the sphere, and the locus where it cuts, that's a circle. So that's one definition, and the other possible definition is, okay, on the sphere you have the notion of distance, right? I mean, because you even have the notion of distance on R3. So a circle in the sphere is just the locus of points on the sphere that have the same distance to a given point, right? And then the obvious question is, okay, are these two notions the same? Right? And the answer is yes. And there is actually a third notion, because you actually kind of refine the observation and say, okay, the way to measure distances in the sphere, it can be done in at least two ways. You can either measure the distance between the points in the sphere using the distance function of R3, or using the geodesic the distance just measured on the sphere, right? Where kind of let's say that you have a piece of fiber, right, of length 1, and instead of measuring in R3 length 1, you say, okay, this length 1 fiber, I put it on the sphere, so it's kind of curved, right? And I say, okay, that's my circle. Right? So you actually have three possible notions of circle, and the exercise is that they all coincide. These three notions coincide. Okay, so this is this exercise. So here, these are some exercises in some circles in the sphere, right? And actually, you can see here a circle in C bar, and part of a circle in C bar, right? So it's missing actually the point at infinity. Okay, and the theorem is that the stereographic projections, so these functions that project from the sphere to C bar and back, that they actually take circles to circles, right? Either of them, like going from the sphere to C bar, takes circles in the sphere to circles in C bar, and going back also takes circles in C bar to circles on the sphere. And then this let me kind of explain the proof very quickly, because I think I haven't done many proofs. I mean, I've been many exercises, but not many proofs. Okay, so going from the sphere to C bar, okay. There is one easy case. If you take a circle in the sphere going through the North Pole, right, and then you see, okay, circle in the sphere going through the North Pole. Okay, consider the plane that cuts it off. Right? That plane that cuts it off passes through the North Pole, right? Passes through the North Pole, but then the way when you look at the intersection with C, which lies at height 0, right, which kind of with the, let's say, with the xy plane, the intersection is the intersection of two planes in R3, right? So it's a Euclidean line. Right? Together with the point that corresponds to the North Pole, which is the point at infinity. So it's a circle in C bar. Right? So that was easy. So circles through the North Pole go via the stereographic projections to circles in C bar. That was kind of the easy case, right? And now let's take now another circle, but now not passing through the North Pole. Right? That is, we take a two-dimensional plane that cuts the sphere, but it doesn't cut it in the North Pole. Right? It cuts it somewhere else. Right? So the first case, okay. The first case, the one that cut the North Pole, was, you can see it was like this one, right? So it's something like this one. This is the circle, and this is the intersection of the two planes that I told you, right? Okay, and now in the other we are in the second case. In the second case, we're kind of taking this other plane that cuts off this circle, right? And now we are projecting here. Right? And now, from knowing that this is a circle, we want to deduce that this is also a circle. Right? So we are in this other case, which is kind of harder, because now this plane doesn't pass through the North Pole. Okay. So, well, what I start doing is I describe the plane as the set of points that satisfy certain linear equation. Okay, and then, well, the next thing I do is, for each point of the sphere, the corresponding point in C bar, I write it this way, right? I mean, kind of the stereographic projection of this point, I write it as a complex number this way. Of course, the real part and the imaginary part then depend on which point I take, right? So that's why I write these sub-indices, right? And then, using the fact that projecting and coming back is the identity in the sphere, right? So that this corresponds to projecting, going from here to here, and then going back, and that's the identity of the sphere. I have this, right? So what I'm doing is, you see, I'm writing x, y, z as q of AB, of A plus BI. Right? So when I write x, y, z as q of A plus bi. On the one hand, I am coming back to x, y, z, but on the other hand, I have to apply this formula, right? Q of A plus bi, Q of A plus bi is here, right? So in the denominator is 1 plus the sum of the squares, and this 2a to be sum of the squares minus 1. And that's what you see here, right? In the denominators is sum of the squares plus 1, 2a to be sum of squares minus 1. Okay, and then you realize that your point is also on the plane if and only if it satisfies the equation defining the plane. So if and only if, with this being capital A, this being capital B, and this being capital C, I'm sorry, not sorry, I messed up there. Sorry, with this being X, this being Y, and this being Z, and here, well, I just plug in, right, and I have to obtain 0, and then I perform some algebraic manipulations. Kind of, this is actually kind of easy, right? I mean, kind of, I just simplify similar terms, right? So, okay, and so this is pretty much an equivalent equation to this one. And then I finally rewrite this equation as this equation, and I notice that this is the equation of a circle, right? Because this is of a circle in C, because this is this minus something, no? minus this square plus this minus something square equal to something, right? That's the equation of a circle, right? And I can actually say which center, right? Well, I read it off from here, and which radius, right? I read it off from here. So what I see is that x, y, z belongs to this circle of the sphere if and only if A plus bi belongs to this circle in C. Right? So it was a bit harder, yeah, it was a bit harder than the previous case, but now I see that this second one is also a circle. And somehow the reflection one has to make now is that actually I proved both directions. Because in the first case, I considered a plane passing through the North Pole. So I'm also proving that everything of the form straight line union infinity goes to a circle. And here I had if and only ifs everywhere. So I actually proved both directions. And then just to finish, just the remark that one can have other stereographic projections. So today what I did was I took the unit sphere, right, and then which has the xy plane kind of passing through its equator, and then I took the stereographic projection from the North Pole. But I could have as well chosen another point in that same sphere, and then I could have asked myself the same questions about, like what does it send circles to circles and so on. Or I could even have taken another sphere, like what you're seeing there, right? Which is, instead of taking the unit sphere at height 0, take the unit sphere at height 1 up, 1 above. And then project from the North Pole, or project from other point, and ask yourself the same questions, at least about sending circles to circles, right? And somehow it's so nice that the story repeats. Okay, and well, you can find some homework. Like if you go to the website, the homework is already there. Okay. Don't be panicked. Like if some of the concepts of today were like too advanced or too abstract, don't panic. You know, I'm going to be less abstract in the next classes. Okay. And I'll see you on Wednesday.